Hi, this is a recording by tutorfy.co.uk. We provide tutors in maths and science. Do check us out. Okay, today we're going to talk about RMS. So, RMS, so as in RMS voltage or RMS current and so on. Okay, so this is root mean square, by the way. Okay, now with quantities that are sinusoidal, like AC voltage or AC current, you may want to know something about averages of these quantities over time, right? Because they're always changing. So let me just be clear about what I'm talking about here. So I'm talking about, something like this, where you have, so you've got AC voltage, so maybe it looks something like that, with the value here, let's call it V0 for the peak voltage here, and here is 0, and of course negative values down here. Now if we were to ask questions such as, all right, so I've got an AC appliance, an AC power source, what's an equivalent DC power source that will give you the same power over time, right? So in that sort of question, you want to have some sense of averages, I suppose, right? That seems to make sense. Now, if you look at the averages for this, you'd see that it's problematic to talk about the averages here, because you have this thing being negative down here, and of course you have the values being positive in these regions, and over time, say over one complete cycle, the average is 0, and that's not very helpful in our analysis, right? So this is where the concept of root mean square comes in, and it's going to be quite useful in many different areas, especially in physics. So root mean square. Okay, now this is named very well, as are many things. We're trying to the people who named this are trying to help you figure out what the thing is. So what do we do here? So what we're saying is that, okay, this value goes positive and negative and so on. The problem really is kind of these negatives that cancel out the positives, right? So why don't we just square the quantity first of all? So instead of talking about V, hey, let's talk about V squared instead, right? Analyze that. So let's really talk about the average. So talk about mean square, right? So talk about average of V squared, and I'm gonna write it with these angular brackets like so to mean average. Okay, so you're gonna see that going forward. So average of V squared, and then remember that what we're interested in is some kind of average for the voltage itself, right? So if you have the average of V squared, what you want to then do is square root that, so that then you have something that's not in volts squared but in volts. So you just take a square root of that average of V squared. Then we have our root mean square, or VRMS. Okay, so that gives us in this case VRMS. Okay, now so let's look at this a bit more concretely. Okay, so again, going from maybe that a little too small, but let's try to work with it nonetheless. So what we're saying is, okay, this is our voltage, our AC voltage, and what we're going to do first of all is we're just going to square it. So we'll square it, and it will look something like that. Now my drawing is not the best here, but and the new value over here, so this value here will be V0 squared. Now this is not to scale or anything like that. It's just showing, when you have 0, of course the V squared will be 0 at this point, and then when it's maximally positive here, the v squared is maximally, it takes its maximum value, and then it goes down to 0 again here. But crucially, when the original v was negative here, we still, the v squared still is positive, right? And you can see kind of the symmetry that's going on here. It's quite a symmetrical, nicely symmetrical graph. Now, if I were to ask you, what's the average of this v squared graph that I've just drawn? I hope you'll agree with me if I were to just say, hey, the average of that is simply halfway here, right? So the average, it should, I hope, be intuitive that average actually is just v naught squared over 2, right? Because the graph spends as much time above above the halfway point as it does below the halfway point, and it's nice and symmetric. So that should make sense. So therefore, we can write down here that v squared is v naught squared over 2. Okay, I'm gonna calculate this value in a bit more sophisticated way using calculus in a second. But if you don't study calculus, this should be enough for you to just to use the symmetry argument to say this is the halfway point. So this is what we have now. VRMS. So here we've got the average of, we're at this point with the average of v squared. VRMS, we need to take the square root of this thing, right? So we need to take the square root of v naught squared over 2, which just gives us v naught at the top and root 2. Because if you take the square root of a fraction, you have to square root both the top and the bottom, and you get that. That's the value. And of course, equivalently, if you're talking about current, for example, AC current, IRMS will also be I naught, the peak current, over root 2, and so on. Okay, so if you are into your calculus, or you'd like to be convinced a bit more about this v naught squared over 2 value, I'm going to do a bit of calculus here, but you don't have to go through this. So from calculus, right? So here we go. A little bit of integration here. So all right, so we have, I'll redraw our original v, right? So it was v naught for that, and then so that means that v equals, in my case, I'm gonna make this you can see it's sinusoidal, of course, and I'm gonna make it it's a sine curve, right? So this will be a function v naught sine 2 pi t over the period here. Okay, so the period, so if you look at one complete oscillation here, this will be the time period from 0. So this is time, and here it's argument here is 2 pi t over t, because then after one period the sine curve has gone through 2 pi radians, which is a complete cycle. So that's what we want. And then of course I'm just gonna attempt my v squared again. So that will look something like that. Oh god, that's not very nice, but something like that. And here you've got v naught squared. Now I hope you agree that v squared is simply v naught squared sine squared 2 pi t over t. All right, so now to find out the average value of v squared, what we need to do is to do a bit of integration here. So what we need to do is to do 1 over the time period times the integral from 0 to the time period. So this is one complete one complete oscillation, and we're going to have v squared, of course, which we said was v naught squared sine squared 2 pi t over t, and we're going to integrate with respect to time here. Okay, so what we're effectively doing is we're saying, okay, when you integrate here from 0 to t, in this case, what we're doing is we're finding the area. So what we're doing here is to say this integration is really, we're finding the area underneath the curve for one complete oscillation of the original curve, right? So this is the area we're gonna calculate. Now, if we want to find out the average value of voltage here, if we divide this area by the time period, that will give us what the height of an equivalent rectangle here. So if you imagine we say, okay, this area here we're going to represent with a constant rectangle here, like, right? Once we found the area from the integration, we divide that area by this length here, which is the time period, we will get the height, which is the average that we want. So that's why we divide by t here, the time period. Okay, so now we're actually going to do the integration here, and you will find that it helps to use the double angle formulae here to rewrite this sine squared. It'll just make the integration a little bit easier. So if I were to use the double angle formula here, which you can find in your formula booklets and such, you'll find that now, and also taking the v naught outside, this becomes v naught squared over 2t integral from 0 to t of 1 minus cos 4 pi t over t dt with respect to t. Now this becomes 4 pi because it's I've used the double angle formula here, so the angle doubles, as the name suggests. Right, so this then becomes v naught squared over 2t, and when we do this definite integral here, the one just becomes a t minus, and the cos goes to minus sine 4t over t, but you need to also divide by 4 pi over t. So this is 4 pi, and you have a t here. All right, and it's a definite integral with these limits here, 0 to t. Okay, now, and we'll carry on with this. So what we'll have is, so this becomes v naught squared over 2t, and then putting in the limits, we have the time period minus time period sine 4 pi time period over time period over 4 pi, and then minus 0, let me be clear there, minus 0 okay, minus what's happened? Okay, minus sine of 0. Okay, and I'll close the bracket there. All right, I'm hoping that you can see that this thing, sine 4 pi, is 0, right? It's 2 complete cycles of sine, so that's 0. And of course this is 0, and sine 0 is 0, so all of this stuff is 0, right? That's 0. So this becomes v naught squared over 2t times t, and then the t's cancel. So we find that the average of v squared is going to be v naught squared over 2. Okay, so at this point we can go back to our definition of root mean square right here. So we've got the average of v naught. We found that to be v naught squared over 2 using calculus, and VRMS is when we take the square root of that and we get v naught over root 2. Okay, so you can pick and choose what method you like here, whether you like the symmetry argument here to just say the halfway point here is going to be the average for the sine squared function, or we can do that the calculus way and we exercise your integration skills there. Okay, so that's RMS. Now, what was the motivation for doing this in the first place? It's interesting in any way, in any case, just mathematically, but much more you will find that we do this because it's got meaning, say in physics questions in particular, and others as well. But so meaning in physics for VRMS is that if you did have an AC source, and I'm going to redraw that sine curve again, V naught, and you've got a sine curve like that, and we ask the question, okay, so this is an AC, power source. What equivalent DC power source would give the same power over time? So this would be the voltage DC power source here. What voltage, which is constant of course, what voltage would give the same power as this AC circuit? Now, if we just said, oh, let's talk about the average voltage of this AC power, we found out, strictly speaking, that is 0 if we just take that. So that's why we're in trouble of saying, okay, well, we're going to have to square it first and then take the average and then take the root. Now, let's see. So here, if we're going to talk about power, so average power, DC power, equals average AC power. That means that V DC squared over R, because we don't have to do anything too special here, because this V is VDC is constant, so yeah, no special stuff to do here, integration or anything like that. And then here we want the average of the VAC squared over R. Now, if we're just interested in what's the equivalent voltage, we can forget about this because this is the same in both cases, because we're going to use the same resistance for the circuits. So, but then we found that average voltage squared for the for an AC circuit is the VRMS, right? That we've just done before. So this is VRMS squared. That's what that is. So this teaches us that the equivalent DC voltage is VRMS, which happens to have a value of V naught over root 2. And you can refer to earlier on in this video as to how we came up with the V naught over root 2 here. And it links to the power, the average power, because of this, because power is related to, I should have mentioned this, power is related to voltage by V squared over R. So if we find the average of V squared over R, that we can use that to work out power, and if we equate these powers, we discovered that VRMS is the same thing as the equivalent voltage in DC. And similarly, IRMS would be the equivalent current also in a DC circuit. Okay, I hope that's been helpful. This has been a presentation by tutorfy.co.uk. We have excellent maths and physics tutors. Do check us out for your tuition needs. Thank you.